Hello, my name is April, and I'm mentored by Dr. Suzanne Olet. My topic is exploring the relationship between environmental factors and slope movement at Hollin Hill. This is what I'm going to go through in this presentation. The first important part of my research is developing the research question. My research question was developed after a lot of exploratory data processing and deciding what is possible to answer with the amount of time and data that I have. This process is documented in the appendix of my research paper if you want to take a closer look. I'll take you through a brief journey on how my research question is developed. So, preliminary research is based on data collected from a local weather station. This is a graph of strain from all the channels from cable segment 1, graphed against atmospheric pressure. The strain data is collected by distributed acoustic sensing, or DAS. It is a distributed fiber optic sensing technology which employs an interrogator that sends pulses of light through an optic fiber. Part of the light returned to the interrogator through a process known as Rayleigh backscattering. The resulting optical measurement of the reflected light can be converted to an equivalent change in strain, and this change in strain is hence recorded and can be used as a quantitative measurement and proxy of slope movement, which is what I did here. What the research question ended up being is how does environmental factors, atmospheric pressure, soil moistures, and soil temperature correlate with slope movement? After graphing many environmental factors, including soil moisture and temperature, atmospheric pressure, precipitation, air temperature, and others, I narrowed down to these three factors because they seem to show a correlation on the graph and deserve deeper data analysis. Moving on to the introduction. This research is meaningful because landslides are hazards present in everyday life. Non-seismic landslides have caused nearly 56,000 fatalities from 2004 to 2016. Where I am living also has a lot of small landslides, possibly due to the humidity and soil moisture from being in Southeast Asia, which has piqued my interest. Some previously investigated factors are soil moisture, which could decrease soil stability. The soil temperature has been suggested to have a negligible impact on slope movement based on data that I'm using. The increase in air pressure causes downward fluid movement, which then increases frictional stress and induces a landslide. This project was chosen because I love data analysis and is involved working with raw data and extrapolating correlation to uncover factors related to landslides. Onto my methods. This is the Hollin Hill Observatory located in Yorkshire, UK, and where my data is collected. The site geology comprises of the Redcar Mudstone, Stave Sandstone Formation, and Whitby Mudstone Formations. Landslide movement is mainly caused by the movement of the Whitby Mudstone and Redcar Mudstone, both known to be prone to landslide. It's observed that in this figure, the minimal strain has occurred at S1, whereas significant strain has occurred in S4 in the rupture zone. Comparing these two cable segments will support my interpretation of how different environmental variables relate to small changes in strain versus larger changes in strain relating to slope movement. That data analysis and processing was completed using the 1 Hz DAS data from Olet et al. I resampled it by computing the arithmetic mean over a 30-minute interval. The 30-minute resampling interval is chosen as it is the same interval as the environmental data, allowing for the Pearson correlation coefficient to be computed. Then I compute the absolute value and arithmetic mean over all DAS channels within each cable segment for S1 and S4. This is to see the mean strain values per cable segment. By taking the absolute strain values, it's ensured that the positive and negative values are not canceled out. For each cable segment, the DAS absolute mean strain and corresponding environmental variable, barometric pressure, soil moisture, and soil temperature are plotted on a twin axis, and the Pearson correlation coefficient is computed based on the correlation function in the pandas library. The Pearson correlation coefficient is then used to evaluate the correlation between environmental factors and the DAS strain. Here, I will go through the results and figures from my paper. In this figure, I observed that the atmospheric data is relatively constant from January 12th, 12 p.m. to January 14th, 6 a.m. Thus, when strain data increases throughout the 3-day period with a more abrupt increase beginning at January 14th, 6 a.m. The strain value increases prior to the increase in strain after January 14th, 6 a.m., and the pressure decreases slightly from January 14th, 12 a.m. to January 14th, 6 a.m., while strain continues to increase. And this is the data from the S1 cable segment plotted against the atmospheric pressure. Now, this graph is of the S1 cable segment as well, whereas the other variable this time is soil moisture. In this figure, the soil moisture remains relatively constant until January 13th, 6 p.m., where it increases. Both strain and soil moisture increase from around January 13th, 6 p.m. To January 14th, 12 p.m. This graph is of soil temperature graphed against the S1 cable segment strain. The initial increase in strain accompanies the matching increase in soil temperature from January 12th, 12 p.m. to approximately January 12th, 3 p.m. However, strain decreases before soil temperature decreases. As the soil temperature decreases steadily from January 12th, 6 p.m. to January 13th, 12 p.m., the strain increases at a steady rate as well. From January 13th, 12 p.m. forward, the strain continues to increase at a steady pace, while soil temperature decreases till January 14th, 12 p.m., and remains steady until January 15th uh, at midnight. Here, I began to analyze the S4 cable segment. Here, strain begins to increase prior to an increase in atmospheric pressure occurring around January 14th at around 8 a.m. It is shown that strain increases while atmospheric pressure is still on a decline at around January 14th, 6 a.m. Note that the y-axis for strain is much larger than for S1. In this figure, the soil moisture remains relatively constant up until January 13th, 6 p.m., where it increases. Both strain and soil moisture increase from around January 13th, 6 p.m. to January 14th, 12 p.m. In this figure, in the midst of the decrease in soil temperature between January 13th, 6 p.m., and January 14th, 12 p.m., the strain started to increase. Using the correlation function from the pandas library, I correlated the Pearson correlation coefficients. A coefficient of around 0.9 signifies a significant correlation between atmospheric pressure and strain for both S1 and S4. For soil moisture with strain, the Pearson coefficient is around 0.4, which indicates a medium strength of association. The negative Pearson coefficient between soil temperature and strain at S1 and S4 indicates an inverse correlation, where an increase in temperature corresponds to a decrease in strain. Moving on to the discussion. Some limitations of my research paper are data processing, the duration of data acquisition period, and data quality. So for data processing, I had computed the absolute value of the strain data and computed the mean to improve data visualization. However, this also omits the variations of strain in each channel. And the Pearson correlation coefficient only evaluates the strength and direction of two variables and cannot establish causation. It also cannot be used for establishing nonlinear correlation between the environmental factor and strain. Hence, it would not show up in the coefficient value if the factor in question does have a nonlinear correlation with strain. Future data analysis should consider the effects of data processing by evaluating the relationships using other measurement types, computing the DAS data as select channels without their absolute value. Another limitation is the duration of data acquisition period. Due to their availability, only 3 days of DAS data were considered in the study. It's a shorter period of time in terms of environmental changes, resulting in uncertainty over longer-term changes. There are also 2 short periods of strain data unavailable on January 14th, which is unideal but does not make for a large limitation, since environmental factors remained approximately constant throughout the periods with no data. The last limitation I'm going to touch upon is the data quality. In this study, I inferred the slope movement from the DAS strain data. However, depending on the installation and coupling of the fiber optic cable with the surrounding information, the DAS strain data may not be representative of slope movement. And moving on to the conclusion, a high correlation is found between atmospheric pressure and strain from the matching increase of both strain and pressure in the figures presented before. While soil moisture has a smaller correlation to strain, there is evidence from the figures that an increase in strain corresponds to higher moisture content. Soil temperature is found to be inversely correlated with strain. For further investigation, research should be conducted in different landslides over a longer time period in order to further study the impact of atmospheric pressure, soil moisture, and soil temperature on strain. Some of the limitations presented in the discussion should be addressed in further work. For example, more extensive data analysis into individual DAS channels could be completed. Overall, these environmental factors represent a few variables that may impact landslide movement. In order to better understand and accurately model these slope movements, these factors should be taken into consideration. The next two slides are my references. Uh, I want to thank my mentor, Dr. Suzanne Ouellette from the University of Calgary, for all the time and effort she put into guiding me. I am really grateful. I have such a patient and knowledgeable person guiding me. This paper would not have been possible without her, and a special shout out to TSI, who had given me this opportunity to grow and think as a scientist. Thank you, everyone, for listening.